Hi guys, this is our project 2 for practical data science. My name's Shane.
And I'm Thomas. So yeah, a little background on our project. As you can see by the title, we're predicting home equity loan defaults. So we found a Kaggle data set looking at home equity loans, which had roughly 6,000 instances in it. There were 13 variables, one of which was kind of the variable we were trying to predict, which was defaulting on your loan or not. Then there were 12 input variables that talked about the person requesting the loan. We were trying to predict whether or not a loan will be defaulted on, which we saw the value in this because predicting a potential loan default early on would prove extremely helpful for creditors who are trying to see if they should approve a loan or not. So we wanted to create a model with a high level of accuracy to do this. We clearly had a classification task. We were able to use supervised learning models since information about the loan defaulting or not was already built into our data set. And kind of looking at the task with respect to the Tom Mitchell equation we've talked about, we have our performance measure, which is the accuracy of our model on our test set. The task is predicting whether or not the loan is defaulted or not. And as the experience, it's those input variables that we put in to our data that are already in our data set. So the models that we used are listed right here, and we'll talk about them more as we get into our model building.
So here's a breakdown of our variables. Obviously, the one we're trying to predict is the bad variable, 1 if the client defaulted and 0 if they repaid the loan. All of our input variables are quantitative with the exception of reason and job. These are our 2 categorical variables. And obviously, when it comes to building models, we have to treat these 2 types of variables differently. So the biggest issue with our data set was the presence of many rows with null values. And this was mostly not a huge problem because in a lot of cases, we could just use an imputer for the reason and job variables since they're categorical. We didn't really want to find a way to impute those variables because it might prove a little bit awkward for making a model. So we decided to drop the rows with null values for the categorical variables. For the rest of the variables, which are quantitative, we decided to use an imputer. Initially, we thought about using the mean, but when we realized that almost all of our quantitative variables were skewed to the right, we decided to use the median instead. This also isn't too much of a problem, but when we saw that some of our variables, such as delinquent credit lines and derogatory reports, had medians of 0, we realized that putting in a value of 0 for delinquent credit lines or derogatory reports might give those rows an unfair advantage when it comes to classification because having zeros for those values is kind of a good thing. So we decided to drop the variables for debt to income because we had about 20% of missing values for that variable, which is a lot. We also dropped derogatory reports and delinquent credit lines because of the median issues that were discussed previously. And we removed rows with null values for the categorical variables. Once we did that, we split our data set into testing and training, encoded the categorical variables with a one-hot encoder, and imputed the quantitative ones with the median.
So yeah, moving on to our exploratory data analysis, as we've talked about before, nearly all of our variables were skewed right, and that was our justification for imputing with the median as opposed to the mean. Most of our variables in our data set showed little correlation with one another, except for one counterexample, which would be the mortgage due and the value of existing property in the data set, which makes sense because obviously a property with a higher property value would have a higher mortgage. We also found interesting relationships when it came to looking at our classification variable with loan requested years on job and age of oldest credit line, among others. So looking at like these histograms, which are the loan years on job and oldest credit line, we kind of found interesting information here when looking at the higher and the lower ends of the data. For all 3 of these, we see that the default rate for the lower end of the data is actually a higher risk of default than the other. Our risk of default across the entire data set was about 20% versus 80% of the loans not defaulting. And we found this interesting specifically with looking at loan because we hypothesized earlier that a higher amount requested for a loan would lead to a higher risk of default, but this turned out not to be the case actually in our data set.
So when we get to building our models, we use 5 different models and tried them out to see what kind of performance they would give. First of all, we chose to try out naive Bayes and logistic regression because when it comes to a classification task, these are often kind of the first 2 that people think of. And especially with logistic regression, we wanted to try that out because it's very well suited towards a binary classification task. We looked into k-nearest neighbors because of the fact that most of our data in this data set is quantitative, and we thought that quantitative data would work well with a model focused around making decisions based on distance functions. Lastly, we chose to try out decision trees and random forests because the way that people decide whether or not to approve loans or not is kind of a decision-based process in itself. Oftentimes when banks will look at someone evaluating them for a loan, they'll look at all their characteristics and credit history and make decisions based off of certain thresholds, whether or not you fall into certain categories, and decide on whether or not you should be allowed to take out a loan based on that. With random forests in particular, we wanted to remove the risks of overfitting that are posed to using a single decision tree as well. So about 80% of our loans in our data set are not defaulted on. So we need to find models that have a performance of better than 80% accuracy in order to kind of justify that learning has occurred based on these models. We also looked at precision and AUC for analysis metrics, and we set up pipelines with a column transformer, with a median imputer and a Wahat encoder, as discussed previously. So here's the results for running cross-validation on our testing data. We saw that random forest did exceptionally well in all three categories, while decision trees also had a fairly high accuracy result. K-nearest neighbors performed about the same in terms of accuracy as just predicting all rows having not defaulting on their loans. So we don't really consider k-nearest neighbors to have added much value. Logistic regression and naive Bayes didn't tend to perform very well at all. So we wanted to see whether or not we could boost the performance of logistic regression and k-nearest neighbors by fine-tuning the parameters, because we did expect these models to do better than they did. So we ran grid search CV on a logistic regression for a varying C parameter, where the C parameter represents the inverse of the regularization strength. However, even with the most optimized C parameter, we were only able to get about a 1% boost in accuracy. So we don't really think that logistic regression could have done much better. We also ran grid search on k-nearest neighbors with varying n neighbors parameter. The optimal amount of neighbors for us was 8, but there's only about 1% boost in accuracy for that as well. We didn't use grid search CV for the other 3 models because it didn't really make sense to do so for us. A lot of the parameters involved with these models kind of involve the amount of time or amount of iteration that these models are allowed to run for. And so we didn't really see that as being useful for improvement.
So now with these improved models that we had for logistic regression and k-nearest neighbors, we were able to do an ROC curve analysis. And again, we could see that the random forest classifier absolutely does the best when compared to all of them. The decision tree also does very well, as we've seen, and logistic regression and naive Bayes both struggle to perform much better than the average, which would just be the 80% that we did normally. They actually perform like worse in terms of accuracy and barely better in terms of like the AUC metric. The k-nearest neighbors classifier also kind of fits in line with the naive Bayes and the logistic regression. So the main takeaway from this was, again, that we couldn't really figure out how to make a logistic regression and k-nearest neighbors seem to perform much better. And again, random forests tended to do easily the best.
So some final takeaways for our project is that the best performing models that we encountered were decision trees and random forests. Again, we think this might have to do with something about how loan processing actually works in real life. And so the whole idea of like kind of having rules and guidelines in place for approval may be reflected here. We also think that logistic regression may have been impeded a little bit by the imputing process, but we are happy with the performance of decision trees and random forests, and we think that those ones should be explored a little bit more in depth when it comes to more research into this field.